everyone. Thank you for this presentation. My name is Ayoub. I'm a PhD student in the second year at Télécom-SudParis. I work with the associate professor and professor for change. And today I'm presenting our recent work, cache allocation, multi-tenant edge computing, online network. So I will start with small introduction to the context of our work. Data generation rate is expected to exceed the capacity of today's internet, and this is why it's important to serve the user requests directly at the edge whenever possible. And in this context, the edge computing consists in deploying computational resources at the edge of the network that can be co-located with some micro base stations or access points. In our vision, the edge is a multi-tenant environment where the resource owner owns physical resources at the edge, and these resources are virtualized and made available for some service providers, which are the tenant. So in our case, we focus on the caching. So the network operator owns cache at the edge and made this cache available for service providers, and it aims to optimize the cache allocation between these service providers in the presence of an encrypted traffic, which means the traffic between the user and the service provider is encrypted. And we note also that not all this traffic is cacheable. There are some requests that could not be stored in, could be not cached, for example, video streams or live streaming. And also, we aim to optimize this cache allocation on up and down systems in an online way. Before going deep into this talk, I'm revealing some of the related work. So, some of the related works are considering that the system parameters are known. For example, the request rate between the user and the service provider, and or the available cache space. Instead, in our case, we assume that no information about the traffic is available. Some of the offline reinforcement learning, which means they train an algorithm and then use it, while we perform an online reinforcement learning where we use the algorithm on a system which is up and running. We also focus on limited resources at the edge, while some other works are focusing on unlimited resources in data centers. And since we are performing the algorithm on an online way, we consider also the cost coming from perturbing the system in this online way, while other works do not only consider the upstream traffic and do not consider the perturbation cost, since they are training the algorithm offline. So we assume that we have a set of service providers that could be video streaming services, and each one has a catalog with the size NP. And for a content C provided by service provider P, the request rate for this content is lambda CP equal to the total request rate between the user and all the service providers, multiplied by the probability that the request is for the service provider P, multiplied by the probability of being cacheable, the object C is of P is cacheable, and multiplied by the probability that the request is for the object C from the service provider B. Rho CP is the popularity of the C from service provider B. So we consider that at the edge, the network operator has a total K slots of cache, and it allocates theta KP to each service provider P. So theta is the amount of cache that is available for service provider P. So an allocation vector is theta K, going from theta 1K to theta PK, where the P is the number of service providers. And the goal is to reduce the nominal cost C nom theta K omega K, which comes from requests that are not served here at the edge, but are served from other remote servers. So basically, we want to minimize this cost, the upstream traffic, the nominal cost. But since this cost depends on omega K, which represent exogenous conditions that can be the amount of requests that the user may request, we cannot directly minimize this cost, but at most we can minimize the expected nominal cost. But even this optimization is not possible, since we don't know the function of the expected nominal cost. So at each time slot, we perturb the system by delta. For example, we add delta slots to one service provider, and we remove them from another service provider. And of course, if we give more slots to one service provider, we will minimize its nominal cost. But giving some slots to one service provider is removing them from another one, and so we need a strategy to give the best allocation that satisfies the best cost. For that, at each iteration, we measure the nominal cost coming from the upstream traffic, and the perturbation cost coming from the fact that if we give a delta slots to one service provider, it has to download from the remote service the most popular content to fill this delta slots. And so we have at the time slot K an instantaneous cost CK, which is the sum of the nominal cost and the perturbation cost. And the goal is to minimize the limit of the cumulative cost, where the cumulative cost is the sum of the instantaneous cost over the time horizon Z. To do so, we use online reinforcement learning, where in this slide I will present the general settings of our algorithm. So we have the space of states S that contains all the possible thetas, where S is the set of theta 1 going to theta p, such that the sum of these thetas is less or equal k, which is the size of the cache. And theta p is a multiple of delta, which is the discretization step by which we perturb the system, and we will see the properties of delta in the next slide. The space of actions is an action is to remove delta slots from one service provider and adding them to another one. So such that theta plus a, so an allocation plus a vector, an action vector, gives us also an allocation which is in the space of states S. The objective is to minimize the expected cumulative discounted cost given by the following formula, where gamma is the discount factor. Among all the flavors of reinforcement learning, we use Q-learning. So for each state action pair, we associate the value Q of theta k ak, which approximates the cumulative cost, and at each iteration k, we take an action ak following the epsilon degree policy, and then we measure the instantaneous cost ck, and we update our Q table with the classic formula of Q learning. The epsilon degree policy is that with a probability epsilon, we will take a random action. This represents an exploration, and with a probability of 1 minus epsilon, we take the best action from the Q table we already have, which means we are exploiting our Q table to take the action. So for the discretization step, delta, a perturbation, as we said, it could be giving delta to one service provider and removing this delta from other service providers. So we will be able only to visit theta, vector theta, only with theta p multiple of delta. So we cannot reach exactly the optimal allocation, but we reach discrete the optimal allocation, which represents the vector theta in S that gives us the minimum of the expected value of the nominal cost. So indeed, the small value of delta increases the precision of the optimal allocation. Since, for example, if we set delta equal 1, we will obtain the exact optimal allocation. But also, with the very small value of delta, we will expand the space of states and we will increase the complexity of the system. In the next few slides, I will prove that for a discount factor gamma, which is sufficiently large, and for k sufficiently large, we will have the limit of theta k when k goes to infinity is the discrete optimal solution with the probability 1. So this proof will be based on these two lemmas. So the first lemma is that any optimal sequence of actions and states theta k ak, we will have an absorbing state theta abs in S, such that at some point k prime we will have theta k equal to this absorbing state for each k after this point k prime. The second lemma is that the absorbing state of the first lemma is the discretely optimal one, provided with gamma sufficiently large, which means sufficiently close to 1. So the Q table, Q of theta A, converges with the probability 1 to the Q table of the optimal policy, which means that the sequence theta k ak based on the Q table converges to the optimal sequence. But since we are doing online Q learning, it means that our sequence of actions is not always based on the Q table, because we will have always a probability epsilon that we take a random action. So despite that the optimal sequence would lead the system toward the discrete optimal, the system in reality may not be there with a certain probability. So we will denote by D the diameter of the problem, which is the maximum number of steps needed to go from any state to another state. And we said that with k sufficiently large, the sequence theta k ak induced by the Q table is converging to the optimal one. So we will have with the probability k, which is the product of 1 minus the probability of taking a random action at time slope k minus I, and I going from 1 to the diameter of the problem. So with this probability, we followed the sequence during the last d time slopes without taking a random action. So if by using the lemma, the first and the second lemmas, we will have theta k is equal to distinct optimal solution with a probability pk, and for k going to infinity, we will have the limit of pk is the limit of the limit of pk is the one when k goes to infinity. So we will have the limit of k of the limit of theta k when k goes to infinity is the discrete optimal one with the probability 1. In addition to Q-learning, we add yes. Yeah. Yes, we will talk about this here in the numerical result. Okay. So in addition to the Q-learning, we add some other techniques to enhance our algorithm. The first technique was to decrease the learning rate, such that we have more Q table updates in the beginning of our of the time horizon, and then we slightly decrease the alpha such that in the end we have less Q table updates, but with keeping the Q updates relatively large. So we do not increase alpha to a value closer to 0. And the second technique is decaying the epsilon of the epsilon greedy policy in a way that we have more exploration in the first 45 minutes, and in the end of the simulation we will have more exploitation of the Q table. So and in a way that we will have a smooth transition between the two phases of exploration and exploitation. The third technique is experience replay, which consists on using the past experience that we had to update the Q table. In fact, we at each iteration we add the state, the action, and the cost to a memory, and then we sample that memory for a mini batch of experiences of size n, for example, and then we use these random samples to update the Q table. So now I will show you the numerical results. So this is the parameters we used for the simulation. So we used the simulation for 3 service providers in the first step. So here the results show that our algorithm is converging to the optimal policy. Our algorithm is in navy blue and the optimal one is in green. And the convergence is after 50 or 60 minutes, and we will converge to the best of our algorithm in 135 minutes. Also, we compared our solution to the state-of-the-art SPSA, which is simultaneous perturbation stochastic approximation, and the results show that our algorithm is outperforming the SPSA. In the figure to the left, we compared our allocation to a static allocation, in which we will give each service provider the probability of requesting this service provider multiplied by the total cache slot. So an allocation where where the cache slots are proportional to the probability of requesting a service provider. The results show that we can guarantee a gain between 20 and 30% in 100 minutes, which means that we also outperform this static allocation. The formula of the gain is showed after the figure to the left. After the convergence, we also study the fairness of our solution. So we define XP as the slots given to a service provider, normalized by its amounts of cacheable objects, and we compute the fairness of the system using the James index as shown. So the results show that our algorithm is fairer than the theta and al. It's fairer than the optimal solution, while they have almost the same cost. We saw that our algorithm converges to the optimal solution, and compared to the theta prop is the static proportional allocation. We are close to this ideal fairness, since this allocation gives each service provider an amount of cache proportional to the request rate. We also study the sensitivity of our algorithm to the request rate and to the cache size. So in the first figure, we fix the cache size and we vary the request rate. So as we see, for a small request rate, we cannot converge toward the optimal solution because we have few requests and we don't have the big visibility on the system. So our algorithm performs well when the request rate is big. In the second figure, we fix the request rate as the one for 4,000, and we vary the size of the cache slots. The results show that for a small cache slots, the proportional our algorithm and the optimal one are very close, because since we have a few space of cache, so we do not have anything to optimize. Also, we valued the number of service providers from 3 to 4, and the results show that our algorithm keeps converging to the optimal solution and keeps outperforming the SPSA and the proportional allocation. Our work in progress is the model-based version of our algorithm. So the quick idea of the model-based is that we store the pairs, the state action pairs, and the value of the nominal cost. We update our model, which is in this case a quadratic regression model, and then we sample n random pairs theta and a, and we calculate the corresponding nominal cost with the updated model, and then we update the Q table with these values of nominal cost. So we performed our algorithm on a small case. This one, as I said, is still in progress, and the results show that the model-based is convergent toward the optimal solution, while it's while in blue we have our current algorithm, which the figure shows performs poorly. This is due to that the model fee is we had so much hyperparameters to tune with the large scale scenario, which we didn't for the small case, since we are interested in only in big scale scenarios. But this is what we are what we will do. We will keep working on the model base now, and actually I'm working on the big scale scenario. So in conclusion, I can say that we proposed an online Q-learning algorithm for cache allocation at the edge between several service providers with encrypted and not all cacheable content. We showed that our algorithm converges quite fast to a configuration close to the optimal one and outperforms the proportion allocation as well as the state-of-the-art SPSA. So current and next steps. So the current step is the model-based version. The next steps is to consider multiple resources and to consider time-varying request pattern. Yeah. Yeah.
Combined on the convergence speed analytically by doing some calculation instead of experiment.
Have the convergence line
of the convergence speed.
Well, to this point,
no, I'm not familiar enough with Q-learning and so on. So just wondering.
Yeah, at least we have proof that the algorithm converges to an absorbing state, but when it converges, it depends also on the parameters. Yeah. For now, I don't have formula to analyze the convergence time of the algorithm, but yes, it could be. Yeah. Yeah, but yeah, I think it's an interesting question to analyze.
And I think there is this convergence rate analysis for reinforcement learning. So maybe we can build on it characterization of our output. Yes, I think it could be possible. Yes.
Okay.
Yes. You said that when you allocate some capacity to a service provider, downloads something, right? That's what you based on for long. Did you consider cases like maybe the service provider has to pay for bandwidth, and sometimes they just won't upload something because they know in advance it won't serve anyone. So can you adapt your algorithm in such a case?
Yeah. In case in our algorithm, we consider that there is no payment between the network operator and the so even the
yeah. Okay. Just my question was that.
Yeah. In another scenario. Yeah.
So if someone says, "Okay, I don't want to download the,"
would be the case that it's paying for downloading such content. It may and it will be not useful for some users. So yeah, he can refuse to download.
In this case, algorithm.
Yes, it is possible. Yeah.
Anastasios?
Yes, can you hear me?
Yeah.
Okay, thank you very much for the nice presentation. So I have two questions.
Just, wait a minute. I think for the sound there is something wrong. I hear you on my PC, but it should not be on my PC, but on. Can you speak again?
Yes, hello.
Still on my PC. Sorry. I just needed to do something on my PC. In fact, I understand now that why the sound was not so good. In fact. It was my PC, in fact, so it isn't. Is it the right one? I think it should be. Can you speak again? Sorry, Anastasia.
Hello.
No, it's not yet well selected. I hear you. Huh?
Hello.
Do you hear me?
Yes, I can hear you.
Okay. Just wait. I do not understand. C'est dans Zoom en fait. Et où après? Okay, no, I think it will be better. Sorry for that.
Okay, yeah.
Yeah, can you hear me?
Yes, perfect.
Okay, great. So yes, thank you very much for the presentation. Very nice. So some very simple questions that I have is that, for example, when you present the convergence of the epsilon greedy exploration policy, I didn't understand how. I mean, is this not? I mean, from my familiarity, this should be normally something standard, right? That the epsilon greedy policy converges for the Q-learning. What is exactly the adaptation of this to the current form? Yeah.
So yeah, Q-learning is proved that it converges in all the cases and all the use cases. But here I prove that we converge to a discrete optimal allocation with a probability 1, which I mean that we are sure that we are going to an allocation that one allocation that it guarantees the best possible cost with a certain probability 1. I didn't prove that the Q-learning converges. The Q-learning converges in all cases to the optimal Q table. But here I adapted this point to our case to prove that with probability 1 we will have at some point we are arrived to an absorbing state, and this absorbing state is the optimal one.
Okay, I don't really understand how this is difficult from the fact that the Q-learning converges to the optimal value, but okay, maybe I need to read more of the paper.
Yeah, okay, it's okay. So the
the
Q table will definitely converge to the optimal Q. The Q-learning will definitely converge to the optimal Q table. But since we are using an online Q-learning, it means at some point we will take a random action. So the action will be not based on that optimal Q table, and we want to prove that despite this random action, that we will be for sure in.
Of course, I understand, but wouldn't that be for any epsilon greedy Q-learning algorithm?
Yes, but in other algorithms they train the algorithm and then they use it. But here we are using the Q-learning in online way, which means that we run the algorithm and we try to optimize on a real system that is really working.
Yes, so that was my second question. What is the difference between offline and online? I didn't understand this.
Yeah, so the offline is basically training a Q-learning algorithm outside the real case. They run it on a simulated system and then they apply it to a real system. But since we have no information about the request rate or the cache size, we cannot simulate the scenario. So we apply this on a real case. We run this algorithm with no knowledge in the first time slots, and it trains himself to adapt to the real scenario.
Okay, I thought that this was how all the Q-learning algorithms would work, but yes, okay, I need to really look more deep into your work. The last question is about the convergence that you show in minutes in the plots.
Yes.
So I don't know if the presentation of the convergence in minutes or in seconds makes somehow very much sense in the intuition to understand what is going on, because this, I guess, has to do a lot with the demand rate, right?
Yes.
So if you have low demand rates, it should converge slower than if you have fast demand rates, I would expect.
Yes, but having a low request rate, since there is no so the network operator who is trying to optimize the allocation doesn't know anything about the request rate. So for a low request rate, we will have no visibility about the cost, and so we will not optimize the allocation. We will not have anything to base our allocation on.
But then would you, based on your comment, would you suggest that there is some, let's say, ideal service rate that is good for your system? Ideal demand rate that is good for your system?
A good demand rate is, yes, I show that in the sensitivity analysis. We found that the ideal request rate for our system for now is 4,000 requests per second.
Okay. Okay. Very good. I will check the paper. Thank you.
Okay, thank you.
Other questions? So thanks again.